Okay, so I think what we did was to do in the last class, we did some very important, we proved some very important things. So I think the most important thing that we were able to, I think we should scroll back down. Yeah, it was here. And what we showed was that you take the partition function, which is a meta observable. And so we started with this partition function z of j, and then we said that this would be equal to e to the power wj. But what I will do is that for good reasons, I would put some I by h bar here. Okay, it's just a matter of definition of wj, right? And what we showed is that log z of j is the generating functional of connected correlation function, right? So we called log zj itself as wj last time, but I would give this definition because many times we simply put h bar is equal to 1 if you want to keep h bar, and it's useful to take I also if you're not doing Euclidean, but in real time. We'll see why this is useful, because it's then easy to see the effective action, define the effective action directly in terms of wj. So then it is quite clear that minus or h bar by I times log of zj would be equal to wj, right? In this way of doing it. Okay, so keep that in mind. And now let us try to directly go to, okay, so maybe we should then recast this thing. So, so firstly, if I want the expectation value of x, expectation value of x we saw in the presence of a source j is simply delta log zj, delta jt. There is also a t here. This expectation value of the measurement of xc in the presence of source j, and this is what it is, right? And then this will be equal to I by h bar delta log zj delta jt, right? So yeah, I don't know, maybe I should, okay, depends on many conventions. Usually all these conventions different conventions are same, because you either put, because h bar is 1, but okay, let me put here I by h bar effectively. Sorry, what I should have written here is wj, of course. So now we can define our effective action, the quantum effective action. This is a Legendre transform of wj. So if you remember so basically the effective action, the purpose of the effective action is that it should give the equation of motion for x, x of t as a function of time. And so this is what it's supposed to do. So then the definition, sorry, what happened? The definition of the effective action gamma of x is simply, let me again, for we put I by h bar. Oh. Yeah, okay, let me put I by h bar on the P here. And I don't know if I should keep this I by h bar or not. I'm just getting, sorry, I have to, maybe, okay, we'll figure it out later. So this is dt, and then j, let me explain this properly, xt. So let me explain what I've done here. So this is standard way to do the Legendre transform. So now here dt should be on the contour if you wish. So this is on the Schwinger-Keldysh contour C. It's a contour thing. And then x is also part of the contour. So x has some value here and some other value here, x1, x2, and x1 is not equal to x2 generally. So this is how we should think about it. But I'm going to simplify this a lot more, very easy. You will see, so I will simply discuss the vacuum case. I will take the T is equal to 0 case, the temperature is equal to 0 case soon. And I will get rid of this contour and just have only one-sided contour. But in general, you should be able to do this. And this actually is this action, this effective action of Schwinger-Keldysh contour is actually the equation for the action for an interacting quantum Brownian oscillator, right? This is the essential. This is if you don't have the, so basically if you don't have no x squared term in the potential, you have only x dot square, then it's a kinetic theory and you have the quantum Brownian motion, but it's a Brownian motion in presence of some potential and then interacting because simply because it has higher order terms like x to the power 4. Or maybe I can, instead of interacting, I can quantum and harmonic Brownian oscillator. So it's an effective action for that, if you wish. So actually, this action can even give you dissipation and all of that. But for the moment, I'm not. We will not deal with this thing. It's a very interesting topic on its own. And actually, Schwinger Schwinger wrote papers explicitly on this subject, and it was like path-breaking papers, which gave rise to the original Schwinger-Keldysh contour. He started with quantum mechanics, actually. But we are not going to, and only recently people have tried to understand this much better in terms of some effective action construction. And it's a very beautiful and simple thing, but maybe we can return to it at the end of the course. Maybe we can return to this whole thing at the end of the course. For the moment, we will do a simplification, but for now, we can just look at the formal argument. So what we have to define what is j of x. So j of x is as follows. So for a given j, right? We obtain xj, right? X in the presence of j with the definition that it is basically delta log gj delta t, right? For a given function j of t, there is a unique function x of t, right? At least if you do Euclidean thing, there will be a unique one. For a given j, we obtain x of j, right? So you can invert this and define jx, right? Which is essentially the j of t, which gives you choose the j of t such that the expectation value of x would, in the presence of this j, would be this would be this desired function x of t, right? For given x of t. Is this definition clear?
Sorry, can you explain this statement again?
Okay. So now for a given j of t, you get x of t, right? Through this functional differentiation. Is this clear, Akshay?
Yes, sir. That's clear.
Okay, then you can invert this function. So you know what? Basically it's a functional. Okay, let me give you this. So what is a function? A function f is something that maps, say, x to y. So given f of x, you find another number y, right? So this is a map between numbers is a function. A functional maps one function to another function. So for example, given a j of t, you will get an x of t by differentiating this object, right? So you can invert this functional now to get, like you can invert a function, you also invert a functional. And the way you do it is simple, that, so suppose you now give an x of t is given to you. I have to find the j of t such that x of t would be equal to delta log z gj divide the functional differentiation of the partition function with respect to jt, right? The log of the partition function with respect to jt. So then, or is equal to, if you wish, I will write that. So given x of t, you have to find j of t such that this is true. And this is what you call jx. All right?
Okay, sir.
Yeah. So basically, this is a functional relationship between two, and if you invert it, you will get x of t. For a given x of t, you will get a unique jxt. So this is the jxt that you should come here. You must have seen all of this stuff, all of these things in basic thermodynamics course, because I think when you go for example, from one ensemble to another ensemble, you do this Legendre transform, right? If you remember. So it's exactly that we are repeating here. So W of j minus dt jxt xt would give me gamma x. Okay, so now let's see why it is called, why it should be an effective action, right? So to see that, let us try to take a functional differentiation of delta gamma x. Let me do one thing, okay? Instead of wj, let me write log zj, because that is, and get rid of this I by h bar for the moment. I'll restore it. I mean, this is not really, this is simply a normalization factor that doesn't play any role. So let me make my life simple. For the moment, let me get rid of I by h bar and restore it later if I need to. Okay, so then let us see what happens if I do delta gamma x, delta x. So I have to take a functional differentiation here, right, and here. So first I should functionally differentiate delta log zj delta x, right? And then minus of, here I should differentiate, if I differentiate x of, I can delta t minus t prime, and this minus of jt, right? And then I have to functionally differentiate this guy also. So then I should have minus dt or d tau. Now, if you allow me to change variables, because j tau delta j x tau delta xt, not tau, and then x of tau. Okay. I simply differentiated. I have simply differentiated this thing. That's all I've done. Okay. And now what I can do here, I can implement the chain rule of differentiation. So the first term I can rewrite as okay. I just simply implemented the chain rule and have to sum over all taus. So I'm integrating over d taus here, okay, because it's a chain rule. Is this chain rule clear, what I've done here? So essentially, the chain rule is like this, that you can either think, for example, you can either think x of t as your, so a functional is actually a function with infinite number of entries, right? Because, okay, what is a functional? It maps, okay, anyway, Okay, I think this should be quite clear to you if you know if you have done all of this stuff. So either you can take x of t or j of t as independent, but then when you differentiate by the chain rule, then you have to take all possible entries because for a functional you need all these inputs. Like for a function you need x, y, z, you need all the inputs j of tau to be able to. So this is what it is. The chain rule is doing here. And then I have minus j of t again. Minus tau delta jx tau delta xt and x of tau, right? Now you see that these two terms are canceling out because this guy is nothing but xj, right? This guy is nothing but xj, and this is delta j delta x tau, and here it is jx instead of xj, but then they are the same thing because either I for a given x at j I take, I mean this is equivalent to taking an x and specifying the j, right? Instead, and or specifying j and writing the x. So these two will be exactly the same thing. So they will cancel out. Is this clear? You may have seen all of this thing already in your thermodynamics course. Actually, this is exactly same manipulations you do to go from. But when you do in thermodynamics, the only difference is that you are not. So you have, for example, you have something that is conjugate variable. So for example, temperature and the entropy density are conjugate variables, right? And here, J, T, and X, T are conjugate variables. They are Legendre conjugate, if you wish. And similarly, the chemical potential and the number density, these are conjugate variables, right? And these are thermodynamic conjugate variables, and you do the Legendre transform. So if you want to go from the microcanonical ensemble to the canonical ensemble, or to the grand canonical ensemble, you will do the Legendre transforms with respect to T and S, right? And then there you see that the partition function, similarly, there is the, okay, we will read the partition function. Instead of J, you would write here some temperature mu and all of that, right? And if you take its derivative with respect to T, if you remember, what is this? This will give you essentially the entropy density, right? And so basically, this is the same manipulations that you're doing there, right? And it's exactly the same stuff that you are doing there. The only difference there is that instead of like T mu, you have infinite number of J of T and infinite numbers of X, because here J of T is a function rather than a number or just a variable, right? So, and this partition function is a functional rather than a function of temperature and mu. It's a functional of J of T, right? So this is but the maths is the same. The maths is nothing different. So this is exactly, so the cancellation again is because here the same for the same reason for a given x. So here x and for a given x you have a J of x, and here for a given so in this here you for a given x you have a J of x in this expression, and here for a given j you have xj. But because they are the same object, because they can invert each other, so this will cancel out. So the moral of the story is that delta gamma x delta x is minus jt. So what it implies is as follows. The implication is profound. If j of t equals 0, then gives the quantum corrected equation of motion for x, right, in the presence of j is equal to 0. So that's remarkable because so it's a very simple proof that the quantum effective action gives the correct equation of motion for x of t. Okay. So this is something that we have claimed before, and now we state explicitly. All right. So any question here?
Sir, the effective action is a function of x or functional of x?
It's a functional of x, of course. There is
Okay.
no x here. Yeah, yeah, but I just simply don't write it because it's understood it's a function. Similarly, there's z is also functional of j, right? J is a functional because j is a function. J of t is a function, arbitrary function, and okay, so fine. All right, so this is up to here. We have, so if you have some very basic questions like what is a functional derivative or something, blah, 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 you can ask Pratik to have a tutorial. You arrange a tutorial with him. I think that would be better because otherwise the flow will be, but I think Akshay, you must have seen this before, right? All of this functional derivatives you must have seen before, no?
Yes, sir.
This. Okay, so now what I'm going to do is to say what is this gamma of x in a more, but as I said in my last lecture, gamma x has a much more beautiful role. But before going to that role, let us try to see what is the form gamma x should take. So firstly, in the limit, h bar goes to 0, right? The gamma x should reduce to simply the classical action, right, of x, right, which is simply half m x dot square minus p of x. It should reduce to this, right? I mean, there is no other way because when h bar goes to 0, we have to recover classical mechanics. But then, of course, it will have all corrections. So gamma of x would have corrections s classical plus h bar s, and it will turn out that each of these corrections would be if a h bar expansion would be simply the loop expansion. We will see why. H bar square S2 loop and all of this. So it will have all kinds of corrections of this form, right? But this is only so far as the H bar correction goes. But there is another way to also see it structurally, which is more interesting, is that I think, yeah, we will use both kind of expansions. And the other thing that we have, gamma of x would have a natural expansion in this form now, which is, yeah, let me put the eyes and everything and do it properly. Okay, so maybe what I will do, gamma of x, I would write down as sum n is equal to 0 to infinity 1 over factorial n, and then dt1 to dtn gamma n, and then I would write this down as yeah, I just want to see if I put in all the factors. Right, so let me see what is the best way to write this one. So what sometimes people do is that, yeah, so one of the things to note here is that this gamma n, maybe what I can do, let me rewrite it in a different way. Let me put this things in for a good reason. Okay. So what is this? What does this mean is that gamma n actually should be thought of as an operator. For example, so let me see what is the operator should look like. So this operator should, at the lowest level, should be simply a number, right? Again, we should. So here, what I can do is do something like a derivative expansion and write in this way. So this is what I would do. So let me put something like this, some notation of this kind. So n would refer to the number of x that we have here, and then I would put a hyphen and a 0. I will explain, and this will be the number of derivatives. And then I will later put another hyphen and write something which will be the h bar expansion. Okay, so let's do it this way: gamma n 0. So this will be first of all just a number, gamma n 0, but then it will have a correction of this form, which is gamma n 2, and then I should have something like dt1. Let me just simply write in this way: gamma n2 and so on and so forth. Now gamma n2 would have this structure, which is say a12 d by dt1 d by dt2, right? And plus a13 d by dt1 d by dt3, and like this, all possible such. So there will be nc2 such possibilities, right? Because it will have two derivatives, all right? And it can act one of this, any two of these x's. Because if you take a two derivative in one of them, you can always do a partial integration and remove one derivative to the other. So this is the most general two derivative term, right? Are you following here?
Sir, can you explain this step again, this notation again?
Okay, let me give you an example. Maybe that is better. So suppose you have let us take 4 x's and explain. Okay, so what are the possibilities? So first of all, I can have some a0 and some a12 d by dt1. So it only acts on the xt1, right? And then d by dt2 and more terms, like 5 more terms like this. And then there could be terms of this kind, which is d by dt1, d by dt2, d by dt3, right, like this, and so on and so forth. And then you can have infinite number of derivatives actually. So this is an infinite expansion. So basically, you can have, this is what I call the derivative expansion. All right.
Yes, sir.
So this is, yeah. Okay, so therefore you will have, so basically the way to think about this gamma n is that it's an operator, right? It's an operator that acts on this xt1, xt2, xtn, and it has this operator has a derivative expansion. And the first term is simply a number. The next term is number times derivatives like dt1, dt2. In general, it can have arbitrary number of derivatives, and you are not, and because of partial integration, some of the things are redundant. So you just keep that in mind, and that's all. So that is the way you can understand gamma of x. Okay, there is yet another way to write gamma of x. Let us, all of these different ways are important. So this is simply taking into account the derivative expansion directly. So that this is the way you should write it, as some the effective potential x. So there is no derivative here. It's simply a function of xt, right? So it could be a very complicated function, but there is no derivatives here. So, and then there would be a correction, which is z xt. It's some something that depends on xt, and then you have x dot p square and plus higher order in derivatives. Okay, this is another way to think about the effective action. So here you have no derivatives, and here you have this thing. So for example, if I'm looking at a static solution for the static solution, we have delta gamma x by delta t, or delta xt should be nothing but delta v effective, or simply v effective prime. I think there should be a minus sign here, right? Sorry. So minus v effective prime is simply a definition, of course, so to match the v. So you define it with a minus sign, so that in the classical limit, you go to the actual the classical potential equals 0, right? It will simply imply that for the static case, it will imply this, right? So if for the quantum case, you will be at the minima of the effective potential, not of the physical, sorry, not of the classical potential, but of the quantum effective potential. This is something that we will compute today. And then Zx of t would be what is called a field denormalization or field dependent. It would be yeah, we will see it has a good interpretation of being. So if you remember, when we are talking of retarded propagator, there was this z by some e square or omega. Yeah, we wrote something like this: omega minus omega star k, right? There are these quasi-particle poles, and this z of k has to do with this z actually. They are related, and we will easily see the relation why they are of this form. So these, and then there will be higher order terms. So I will soon say what is this, why this Z has this physical interpretation of being residue of quasi-particle poles or related to residue of quasi-particle poles and so on. So all physics is actually contained in the effective action. That's the beauty of it. I mean, there is nothing. So it's basically the physical action that captures all kind of quantum phenomena that you need to do compute, because it's okay. The reason for that will come soon, because it gives the definitions of the actual physical vertices. So we are going to talk about it. But for the moment, you see that there is this particular expansion. So all of these expansions are essentially many ways to look at the same thing. So for example, if I do the h bar expansion here, then of course at the leading order there will be the effective potential will be the classical potential. Then there'll be a 1 loop correction and 2 loop correction to the effective potential. And similarly, this object z of xt will also have, in the classical limit, is simply half 1 over 2m, and then there will be this corrections to 1 over 2m, like 1 loop correction, 2 loop corrections, so on and so forth. So okay, so one of the interesting things is as follows, that yeah, one goal of one major goal is to be able to compute to be able to compute so what you want to do is that physically this expansion is more relevant than this classical expansion. The reason for that is that typically you look for phenomena that have low velocities, right? So if x has very small velocities, and then the higher order terms are suppressed by some power of c. If suppose you're looking at the relativistic theory, for example, so here the higher order terms are suppressed by powers of the speed of light. And so you would be very content just to look at the first few derivatives, first few derivative terms, and build your predictions based on this sort of an effective theory, right? Then the goal would be to get this low energy effective action exactly to all orders in h bar. That would be the goal, to all orders in h bar. But this is something that we cannot do even in quantum mechanics. It's very, very hard to do it, right? And in quantum mechanics, it would be possible to do it in something. It is possible if you do some, okay, for some special theories or some special class of examples, you might be able to do it. But typically, even in quantum mechanics, it would be a very hard thing to do. Okay. But this is remarkable that it is possible to do it even in gauge theories. So Seiberg and Witten was able to derive the exact effective action up to the quadratic order in fields in a class of gauge theories, and in this class of gauge theories, the low energy physics actually is captured by some Higgs phase, where certain gauge group gets Higgs, and you have a space of vacua. And so they were able to derive this effective action for all classes of such vacua, all vacuas. In all of these vacua, symmetry breaking vacua, they were able to compute this exactly. So that's like a very remarkable achievement, and like that's sort of a like reaching Mount Everest in quantum field theory. Okay, if you think there are many such peaks, Mount Everest probably is not the highest. So far, all the highest peaks that we have seen, that is certainly one of the highest peaks in quantum field theory that has been ever scaled. So there are, of course, many peaks which have not been scaled yet, but this is one of the biggest peaks that we have been able to scale, to be able to compute such things exactly. But certainly such things are very advanced, and we cannot include them in the course. Maybe we can discuss a little bit in the next course. But this is the beauty of the subject, that you see. But the thing is, the goal would be to compute the Eulers and H-bar, but this is not possible. But hard. So what we will do, we will compute this object, at least the V effective potential, to one loop order. So that is what we will see today, how to do it. That itself is quite a challenging thing. I mean, for a beginner at least, to understand how this computation should be done. Okay, but before that, so now we see that there are these three different ways of understanding thing, and so all of these three would be important for us. So one thing is, this is called a loop expansion, and we will show why this is a loop expansion. Or for the moment, you can think of it as an H-bar expansion. And this is an expansion simply in terms of this, right? So for example, if you want to get the effective potential here, so that would have infinite number of such vertices, because you can take the numbers which has no derivatives for each n and sum all of them up, and that will give you the effective potential, right? So it already has an infinite number. So this is called the vertex expansion, if you wish. And this is what we will call the derivative expansion. Okay, so the derivative expansion is the most physical thing, because when you want to derive anything, but vertex expansion is also important. So so this is what we will see, and because these are the proper vertices, so to understand renormalization, these vertices would be important. So is it clear, these three expansions of the effective potential of the effective action? Very good then. Okay, then let's go to the next thing. So what we would like to show, the effective action as a dual meaning is the generating functional of one pi vertices, or often these are called proper vertices, proper or physical, whatever you could say, vertices. And this is something that I already defined in the last lecture. So proper vertices are essentially one pi vertices, as the name suggests. So these have these have no external legs, but you have like three external circles where you should 1, 2, 3, where there should have been an external leg, but simply not there. So basically, what you have to think, there is some x cube. Suppose your terms have x cube or x to the power 4. There could be x cube or x to the power 4, and there could be as many lines as possible which will connect to j's, right? So that's the way I drew it last time. Suppose you have x to the power 4, for example, you can have, this would be a proper vertex, right? And then this would be what I call 1, 2, 3. And if I write gamma 1, 2, 3, it would, I have to strip these things off and there simply have these objects, right? So this is a vertex because the way to think about it is as follows, that if we have these external lines J, right? They would, and I can think of this as I can replace the whole thing by a vertex now. Now this is a vertex because it can have all kinds of derivatives and blah, 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 right? That acts on these two things. And so this is a proper 6 vertex. I can, I can reduce the loop and replace it by a vertex, right? It's a 1 pi 6 vertex. And then what I was able to tell you that if you remember that any connected diagram could be constructed from exact propagators and 1 pi vertices, because you can take you can think of like this exact propagator, and then you have this proper vertices. It already includes all stuff. So this is an example, say, of a 4-point function where all the corrections to the legs are here. So all kinds of corrections will occur here, and all possible corrections to the vertices are already absorbed in the 1 pi vertex, right? Yeah, and we also saw that you shouldn't overcount. For example, in the one, when you define the 1 pi effective vertex, you will not call this as 1 pi. This is not 1 pi, because this part can be absorbed in the correction to the 2-point function here, right? So this part can be already absorbed in the exact propagator G, and you should not, this is not 1 pi, whereas this is 1 pi. This is 1 pi if I just take this into account in X theory, okay? So this is the definition of the 1 pi vertices, and what we will show that when I do this expansion of this thing, this gamma n's are nothing but, with all the derivative corrections put together, this is the nth proper vertex. Right? So basically that it has a dual thing. So what it means is as follows, that another way to put it as follows. So W of J can be obtained just using tree diagrams from the action gamma x plus xt, or if you, maybe here I can write it in a different way, plus xt j of t pt. So because you can see, so what I want to say is that right, and then if you simply, well, this is something that is obvious, but okay, I have to, I will explain what I mean by this statement. So the main point is as follows, but the statement what is more important to us is simply that gamma of x is going to give you the proper vertices. And furthermore, what you can see is that the exact propagator, let me first prove this statement. The exact propagator is equal to the connected correlation function, is the connected, simply the connected 2-point function, right? All right, it's simply the connected two-point function, the exact propagator. No. So this is equal to delta log zj delta jt1 delta jt2, right? Because it is a generating function of connected propagators, so connected correlation functions, and this we will show is equal to actually the inverse of delta gamma x delta xt1 to delta xt2. So essentially, it means that now what is this object delta x gamma x, this thing? So if you can easily see from the definition of the proper vertices, right? From the definition of the proper vertices, let me rub out this part. From the definitions of the proper vertices, it's clear that gamma n is equal to simply delta gamma x, delta xt1, delta xtn, right? All right. So this proper vertex is simply the functional derivative of delta gamma x. Because if you do that, if you take the functional derivative here, you simply get gamma n, right? It's simply like a Taylor expansion in function space. And therefore, if you just simply take a derivative of the effective action with respect to x n times, you get this proper vertex gamma n t1 tn. So so now this is therefore nothing but another way to say it, it is equal to gamma 2 inverse, right? It's simply the inverse of gamma 2. Okay, so let's prove this first, because this is very easy to prove. So let us prove. So the proof is rather simple, that we take apply chain rule. So if I do delta jt and delta x tau and delta x tau delta jt prime d tau, right, and integrate over all tau, what I should get is simply delta jt delta jt prime, which should be nothing but delta t minus t prime, because jt and jt prime are independent variables, because the value of a function at every point of time is independent. It can be independently chosen. And the functional is simply takes all the values of all of these points as an input and gives an output, which is a number. So that's the definition of a functional. The functional is a function with infinite number of arguments, and the argument here is simply the value of the function at each point of time. So anyway, so this gives you delta t minus t prime, and by chain rule. However, we know that delta of j, right? This implies that here delta, but j is nothing but delta gamma x, delta xt, and delta x tau, right? Because I've simply used here that. Okay, so maybe I think there is a minus sign I missed. Minus of the, there's a minus sign because delta gamma x, right? I simply used that delta gamma by delta x is minus j, right? This is something we just proved. So this is what I've done here, and then delta of x tau, x is nothing but okay. So here I've used that. Here I've used this, and here I've used that delta log say dj delta j is equal to x. So that is what I've done here, right? And so here by x, of course, I mean x at j. Otherwise, there is no meaning of the functional differentiation, right? And here by j, I mean jx, right? Otherwise, there is no meaning. The functional differentiation would have no meaning right? What you mean is this. Okay, so then I simply put that because this is Jx and this is Xj. All right, so when I do that, then this implies so it has to be equal to delta t minus t prime, and this gives us a desired result that this implies that gamma 2 x tau times the 2-point function exact propagator tau t prime has to be equal to, if I integrate over tau, this is equal to delta of t minus t prime. All right. So from here, it follows that gamma 2 x tau inverse is equal to minus g of the exact 2-point function. Sorry, what else are you saying here? Sorry, t, it should be t, and this is t prime, and this is t tau is tau t inverse. So in a short form, it is gamma 2 inverse is equal to minus g2. So what does it mean actually? So normally what you do is as follows: when you write a classical action, right? What is gamma 2? There's a classical value of gamma 2 is as follows. You can write it in this way. It is del tau square plus m square, sorry, minus m square omega naught square. And here probably del tau square by 2m, m square omega naught square by 2 x tau, right? Or x tau square d tau. All right, plus order h bar. So now your propagator is simply the inverse of this, right? So it's basically it's inverse of omega naught square, sorry. So suppose it's easy to see that if you are in this contour, only in the upper part of the contour, and I go and I take, so there are two contours, like, and this upper part and lower part, and I take temperature is equal to 0, then this is nothing but my desired Feynman propagator, because if I do its inverse, it is omega square minus omega naught square, essentially, right? This is essentially omega naught square, omega square minus omega naught square. Okay, I'm discounting this factor of m and all those things which will work out. And if you remember, the Feynman propagator in this limit was simply omega square minus omega naught minus I epsilon square. And this I epsilon simply comes from the correct way of inverting this function. So if I do it in the, because I'm putting the time order prescription, that's the only way you can invert. The inversion would give me that. So in the limit, I simply get my propagator to be the inverse of this gamma 2, of this functional operator gamma 2, right? There is also another way to say it. The another way to say the same thing is as follows. If you remember, for the quantum harmonic oscillator, we proved that del tau square minus omega naught square of the time order propagator. If you remember, we proved this in class, right? X tau x0 is equal to delta tau. And there is a factor of h bar by m and blah, blah. But okay, okay, you can actually absorb all of that in this. I'm just writing schematic. This is something we proved. Remember, we showed that this is true by working it out. We used the Heisenberg equations of motion for the quantum harmonic oscillator, and we showed that this is true. That this is true. Now this is nothing but the classical. At the leading order, this is G2, right? And at the leading order, this is gamma 2. So basically, what you show here is that gamma 2 G2 is equal to delta, is equal to identity in a functional operator. So if you think, because T and T prime are like matrices, so this is like a matrix with infinite dimensional matrix with infinite number of T's, infinite number of taus. So it's a infinite dimensional square matrix, and similarly this one. But if you think in the matrix multiplication sense, gamma 2 times G2, there's a minus. If I take appropriate factors of I and everything out, I'll get a minus because there's a minus I involved here. There is, just forget it. I mean, this is something that you can work out based on your earlier notes. And the main point is as follows, that this is something that we already know at the level of the quantum harmonic oscillator without H-bar correction. Where actually in quantum harmonic oscillator, there is no H-bar correction at all. It's simply the classical thing. And this is something that we already know to be true for the quantum harmonic oscillator, okay? But the statement is that now the exact propagator would involve all possible corrections, all possible self-energy corrections now. So the Feynman propagator would involve all possible self-energy corrections of this form, right? And then you have and similarly, you can understand the proper vertex. So the proper vertex here is something that will receive corrections to all orders now. And if you do that all together, then gamma 2 times G2 has to be equal to, they have to be inverse of each other. So that's the proof that we can easily see. So all of this is simply a more general version of something that you already have seen, right? In the quantum harmonic oscillator. Okay, so now what we need to do is to show that, so what we see is that exact propagator can be obtained from gamma x. So we can get the exact propagator from gamma x, since gamma 2 inverse is equal to the exact propagator itself with a minus sign. Now we can also show that exact 1pi vertices can be also obtained from gamma x. This is something that we are going to prove now. So all the 1pi vertices can also be obtained from gamma of x, right? And then we are done. It implies that any observable can be computed, or any connected correlation function can be computed from gamma x alone, because we know that all so any diagram that if you want to compute anything that suppose we want to compute delta cube wj, delta xt1, delta xt2, delta xt3. So this would be a connected 3-point function, right? A connected 3-point function. But a connected 3-point function can be obtained from these exact propagators and gamma 3, right? So schematically, if I write G2 cube times gamma 3, that should be my exact 3-point function, right? What we are going to do, we are going to prove it now, prove this right away. But the point is that G2 is something that we already know is gamma 2 inverse, right? And gamma 3 is something that we can directly obtain from the 1pi effective action. So we can easily compute all connected correlation functions. So WJ is not really a very nice way to compute things, right? WJ is not the correct, the right way to compute things is to know the effective action. And then in terms of this, to write it this way. And this is conceptually important because from the effective action, we are only considering tree diagrams. We are not, once we have the effective action, we can simply think of this as a tree diagram, because you have this all the exact propagators already in gamma 2 inverse. You don't have to consider any loops, because all loop corrections are already are all here, and all loop corrections to the vertices are already put in here, right? Everything, all loops are already here. There is no need to further take into any loops. So for example, if I know gamma 3 exactly and gamma 2 inverse exactly, I would be able to compute this thing, okay? Now, this is physically very important because that tells you that for all physical computations, we only need, or the most important quantity is simply our effective action. And this would be the key thing to understand renormalization, because this is actually the physical vertex, if you can put it. Because the reason for that is that in the quantum harmonic oscillator, you have seen there is no really H-bar corrections, at least in t is equal to 0 limit. The classical propagator and the quantum propagator is more or less the same. Basically, it means that So all the loop corrections essentially that are what gives you H bar correction, right? So now basically that you can think of the effective action as a renormalized classical theory, right? Because if you want to just simply compute, so you can simply say your classical parameters, your classical potential and the classical couplings have now changed to some new quantum values. And once you take that into account, then you are done. So that's exactly like saying that you have some mass put in some water, and the water has renormalized the mass of the ball, because if you now take action of gravity, it feels a little bit less weight, right? And that is what is happening here, because now you can use if you just want to see the motion of the ball under gravity, and you kind of ignore the perturbations of the medium and all of the stuff, you could just simply write a new effective theory with a new mass of the object. So that's exactly what is happening here. And all correlation functions can be obtained just from this classical effective action. So let us first try to prove this. All right, so this statement that, so for that, let us try to then start with this thing. So maybe I should write log of Cj, because Wj could be either, I can have some. Okay. Now, yeah, so what I should do, yes, so, right. So this is equal to delta by delta JT1 times the way to do it would be to put in delta log Cj, delta JT1, JT2, delta JT3. But what I want to do now is to bring in so this is simply a way of rewriting is, but in the next step, what I'm going to do, I'm going to take into account, this is delta gamma x, delta xt2, delta xt3, and inverse of that. All right. So let's call this matrix some m, right? So, right. So, yeah. So now what I'm going to do is, 1 second. So this is essentially m inverse, and and then the trick is to see that if I take if I take del 1 m inverse, this schematically I can just write delta j by jt1 as del 1 m inverse. This would be equal to, if you wish, let me try to see. Okay, but first, okay, maybe I should do the another thing before I do this trick. The other thing that I should do before doing this trick is to again apply the chain rule, which is d tau delta. So first I should do it delta by delta xt1, delta by delta x tau by delta jt1 times delta by delta x tau. Now I can call this gamma 2 inverse. Okay, this is gamma 2 inverse, this delta by delta x tau of that. Now I can use this trick to compute to do the computation. So first of all, you can easily see this object delta x by delta jt1 would be nothing but g of tau t1, because delta x is nothing but delta log zj by delta j, and it becomes a 2-point function. So this is, and then I have delta by delta x tau of gamma 2 inverse. So now, so what I would do is to take this thing, the del tau of M, if I call this M, M inverse would be equal to del tau M, right? Times, let me, yeah, 1 second. So yeah, okay. Yeah, so this, what I need to do is to show that I have to convert this. Yeah, okay, right. What I want to show is if in terms of functionally, this is the way it should work, okay? That's easy to see because if I multiply this by M, M of del tau M inverse, right, should be equal to, okay, let me, okay, that my goal would be to show this, and the way I will show this is using the fact that M inverse is equal to identity, right? So if I take del tau of M inverse, this has to be equal to 0. So del tau M times M inverse plus del tau M inverse, sorry, I should have, plus M del tau. So these are matrices, okay? You are multiplying them. So M and M inverse are matrices. So when you are multiplying them, and del tau M dot M inverse is a matrix multiplication plus M dot del tau M inverse has to be equal to 0. So now if I take, this implies that if I now multiply both sides by M inverse, I get del tau M inverse should be equal to minus of M inverse del tau M inverse. Okay. So what am I doing here? What is that? Okay, sorry. So del tau M inverse is this. So now what I have to do, I have to use this here. So which means that delta by delta x tau of gamma 2, and gamma 2 is a matrix, and the entries of gamma 2 are T2 and T3, right? This would be then equal, this is inverse, right? So for that, that should be equal to gamma 2 T2 prime inverse, and then gamma 3, so of tau T2 prime T3 prime, and then gamma 2 inverse, sorry, gamma 2 of T3 prime T3 inverse with a minus sign. All right, is this clear? It's simply, and just follow through the definition of this stuff. Okay, so this is, so I just simply follow through the matrix multiplication rule here, and that's what I got. But now, of course, then what I have to do, I have to, because it's a matrix multiplication, there is an integral. First of all, there's a minus sign, and then there's an integral. The two integrals over T2 prime and integral over T3 prime. Is it understood? Okay, I guess you are following it. So then what I will do, now I know this is the exact propagator. Gamma 2 inverse is the exact propagator, right? So then it follows that delta by delta x tau of gamma 2 T2 T3 inverse is equal to minus, and then here I have a T2 prime integral, a T3 prime integral, and this is the exact propagator G2, T2, T2 prime, and then the exact propagator G2, exact connected propagator G2, T3, T3 prime, and then I have a gamma 3 times tau T2 prime, T3 prime. Okay, so this is what I proved now. So now if I substitute it back in this equation, what do I get, right? So this is a connected 3-point function. So substituting back, we get, or we obtain gamma 3, sorry, this was exact, this is G3, G3, T1, T2, T3 would be equal to, so there is one minus sign here, but then there was another minus sign here, which are, there should have been another minus sign somewhere. X by 51. Okay, no, there is no minus sign. Sorry. Okay, I have to take into account. Okay, the minus signs should be taken in. Okay, there is a clever thing of you add i's so that the minus sign exactly comes out very easily. That's why you have an extra i's often. So that we will fix in the next class. For the moment, this class I didn't take into the i's very seriously. But anyway, so here there is no minus sign indeed. So if I take gt, so this is the exact 2-point function, g tau t prime. So I simply have to add it back. So there's an extra tau integral. So then there is a minus tau integral. There's a t2 prime integral. There is a t3 prime integral, and then their exact 2-point function tau. Sorry, this was t1. So I can then change tau to t1 prime, right? I can convert tau to t1 prime. Okay, first of all, it's a symmetric matrix. G2 is always a symmetric matrix. Because a symmetric matrix, I can interchange. This I could have also written this in this way. Sorry, as T1 prime, and call this T1 prime instead of tau, and this would have been then T1 prime. Okay, so that makes my life a little symmetric. That is what I will do, T1 prime, and then we have G2, T1 prime, G2, T2 prime, and G3, T3 prime, and then we have a gamma 3, T1 prime, T2 prime, T3 prime. Okay. Now, if I convert into diagrams, it simply means that so this is exact relation. This is something exact. Okay, this is no corrections or anything. This is an exact functional relation. So it means that the 3-point function can be expressed in this way diagrammatically. We have these are the exact 2-point functions, the exact propagators. G2, G2, G2. They come from T1, 2, 3. And this I can call 1 prime, this vertex 2 prime, this vertex 3 prime, and this is my gamma 3. Okay. So now by graphical argument, gamma 3 has to be equal to the 1 pi 3 vertex, the exact 1 pi 3 vertex, right? Because this is the graphical argument we already gave, that the 3-point function can be written in terms of these 2 exact propagators and the 1 pi 3 vertex. Okay, so this is a way. So what we have proved. So this means that so this is proved. So we have proved that the gamma 3 is exact 1 pi 3 vertex. So now you can generalize this. I won't do that. There is a very elegant way to do this to all orders using path integrals. I will return to this in the next course when I do the path integral formalism. But for the moment, I don't want to generalize it. I mean, one doesn't require path integrals actually. You can easily generalize this argument. So graphically, what is happening? See, firstly, you see that the three vertices, the 1pi vertices, can only be n greater than equal to 3. You cannot have right. This is two vertices is already included. So now if you want to compute something like this, so you would get you might get something like that. Say this is a gamma 4 and gamma 3. That is one way you can get a 5-point function, for example. And so that will give you a gamma 4. And so each of these diagrams can be converted to a functional differential equation. So for example, this will be, the analog of it would be analyzing delta log zj and delta jt1 to jt5, right? And then seeing this is a product of 3, gamma 3, gamma 5, and then these 1, 2, 3, 4, 5, 6, g2 to the power 6, right? You should be able to do the exercise, the same kind of exercises that we did here, and generalize. Okay, so maybe in the assignment, I will give you to verify this for some higher order. You can have fun with it. So what you can show with this kind of arguments that that gamma n is nothing but the nth exact 1pi vertex. Okay. So that would be the main. So that is the main lesson that we learned from here. Okay, so now a little bit of conceptual issues is as follows. So so one of the things is that if I think of so suppose if I define anything as a functional differentiation in this way, JT1, JT2, JT3, right? Anything like this. So this functional differentiation commutes, right? Because some del V, del X, del Y, if you remember, same as del 2 V, del Y, del X, differentiations always commute. So basically, this should be then, the only way this can happen is should be some contour order stuff. For example, the contour order stuff is permutation invariant. So it's invariant under all kinds of permutation. So any contour order thing would be like that. So that is consistent with each other. And similarly, the gammas are also permutation invariant. Okay, the gammas by definition are permutation invariant. So these are very important important points. And there is one more thing I want to say before I end is that there is a simplification at 0 temperature. So suppose I am at T. Suppose I put all my external points on top contour. So this is my Schwinger-Keldysh contour, right? Up, top, and bottom, right? But I'm interested in endpoint functions. So I'm interested only in time ordered, usual time ordered correlation functions of xt1, xtn. If I put everything on the top contour, it's the usual time ordered, right? So then there is something interesting that happens. So what you have to do, you have to basically sum over all possible diagrams, right? All possible diagrams. And obviously you get 1, 2, suppose you have 3 external points. And then you would get all possible diagrams of this kind, which is 1', 2', 3'. But 1 prime, 2 prime, and 3 prime can be either on the top contour or at the bottom contour, right? The statement is we can forget the bottom contour completely. That is, if you're interested, so essentially, if you take trace rho, right, trace rho beta, and then you take t goes to 0 limit, it is nothing but the vacuum density matrix, right? Sorry, this density matrix becomes t is equal to 0, just the vacuum density matrix, because all the other things decouple, e to the power minus en by t. When t goes to 0, en is greater than 0. That's how we always normalize our energies. If that is the case, then this goes to 0. So only except for en is equal to 0, which gives you, so we always take the ground state energy to be 0. And that is the only thing that contributes. So essentially all our, so what we have we're doing, the trace rho beta and time the contour ordered of xt1, xtn simply becomes the exact vacuum. This is the exact vacuum, not the perturbative vacuum, not the vacuum of the, it's simply the vacuum expectation value of the time ordered. So here, of course, I'm taking, I'm assuming all of them are in the one contour, so on the top contour. So the usual time ordered. And then the vacuum, exact vacuum expectation value, right? So is equal to the vacuum expectation value of time ordered correlator. Okay. So this is what we are interested in. So in this case, we can simply not talk about the other contour, which means that all my propagators would be only time, the usual time order. So that is why if you look at Peschke, Schroeder, or any other usual quantum field theory textbook, they're only interested in the usual vacuum correlation functions, because there is an LSZ theorem that tells you that all S matrices can be obtained just from the vacuum expectation values of the time order correlation functions. So you don't, and so all the propagators would be the usual Feynman propagators. You don't need to take into account all this 1, 2, G less, G greater, and G anti-Feynman propagator. So let us see why. So for this, it's easy to do a graphical argument. So first of all, to note that G greater in the limit t goes to 0, right? If you look for the harmonic oscillator, it has only one possibility, delta omega minus omega naught. There was a term delta omega plus omega naught that could go to 0, because that is 1 minus NB multiplied by NB omega naught. Only this term will survive. So it has only support in the positive frequency. So basically, the other way to say it should be proportional to theta omega. It has proportion. It is support only at positive frequency. G less would have support only in the negative frequency, right? And that is all we need now, because suppose we have all our external legs, one in the first contour. In the here, I mean, so all of them are in the top contour, which is a plus contour, okay? And then suppose there will be some graph, and we are taking only connected correlation functions. So these, let us say this part of the graph has the minus vertices, as the vertices that have, these are the vertices that we're integrating over. So there are, of course, and the rest of the diagram will have only plus vertices, okay? Okay. So now you see that each of this thing, because G plus minus is proportional to theta omega, right? Sorry, G plus minus is essentially G less. G less would be proportional to theta minus omega. It will be proportional to theta minus omega. So all of these lines would be proportional to theta of minus omega, whatever the lines are carrying, right? But look, these part of the diagram has no external vertex, right? So the total momentum that flows in should be conserved. It should be 0, because it has no external vertex, right? So the total momentum that is flowing in, because each of these vertices have momentum conservation, and the external momenta are only flowing in from here and not from here. So essentially, all the total, whatever comes in will be going out, right? Because so what I mean by that is as follows. So suppose let us look at this part of the vertex, right? Because here you have omega 1, omega 2 plus omega 3. These are the total thing that comes in is 0, because we, as we showed earlier, there will be moment energy conservation at each vertex because you're integrating over 2. So similarly, you could also say that if I have say this thing, and if I would have looked here, then also there would be a total energy, because there is because whatever flows in has to flow out, right? So so that's the generalization. So similarly here, whatever the total things that are, because here there is no external vertex. Now, of course, if I take this part of the diagram, if I take some, if I take some this part of the diagram, then it will not be true, because there's some overall thing that is flowing from here. So now if the total thing that comes here is 0, so we have, say, omega 1 plus omega 2 plus omega n, all the things that flow here should be proportional to 0. But each of this line has a theta minus omega 1 factor, theta minus omega 2 factor. So now if all of these numbers add up to 0, right, at least one of them has to be positive. And therefore, because it has a theta minus 1 and all this, so this thing has to vanish. If any one of these legs vanish, the whole diagram should vanish. Therefore, the conclusion is that the only diagrams that survive are those which have plus vertices only. And this reproduces the standard rules or standard computational rules that you get in all elementary textbooks, that you only have the usual time order property. Okay, so so that's a very nice conceptual thing that you see. So there is a lot of simplification, and this is something that we will use. So our goal tomorrow would be to compute, or next Saturday. Okay, the goal would be to compute basically V effective X for this Hamiltonian. So we'll compute it, and that would be so. And once we know how to compute it, we can then use it for renormalization. And this is something that we will see for. So the statement about renormalization should automatically follow, because if you can use the 1p effective action to compute any physical quantity, and you're only using tree diagrams, there is no divergence that comes from loop integrals here. So these are the actual physical vertices, because your 1p effective action is a renormalized classical theory that you are using, and therefore it has to make physical sense. And this is a starting point of understanding the physics of the thing. There is something very closely related to the 1p effective action, which is called the Wilsonian effective action, which is almost the same but not exactly the same. But we will come to it. But the 1p effective action again is a starting point for the discussion. And the Wilsonian effective action will lead us to the concept of the RG flow, which is a notion of an effective theory at each scale of observation or each resolution of my apparatus. All right, so that is a good point to stop today. And I went slow again deliberately because many people couldn't join directly. Okay, so have a nice break, and I see you in a week then.
Sir, I have a question.
Yeah.
Regarding the assignment, actually. So you said that.
I can't hear you. Madhav, I can't hear you.
You said that we could
Again, I can't hear you. I heard the first one.
Yeah. Okay. I'll just type.
No, now I can hear you. You can attend. Okay, no, you can. Okay, I just simply didn't change it. If you want, you can change. But I think Madhav, as far as I look for your case, it looks already okay. If you don't need to resubmit, right? I mean, okay, I didn't look it very carefully. If you want to resubmit, go ahead. But no, you can simply resubmit on the directly in the Google Classroom itself. Just resubmit. But today is the absolute deadline. I mean, anyway, it was supposed to be in the last week, so already during the weekday. So I'm not teaching for until next Saturday. So I think it's a good thing to conclude this week. Okay, very good. Then see you next week, same time.